Let us continue with our video lecture series on response spectrum analysis, and this will be our second video. In our first video, we discussed on the theoretical basis of response spectrum analysis. We discussed on some concept, and in this lecture, we will look at some codal provisions for response spectrum analysis. And these codal provisions are based on IS 1893 Part 1 2016 code, which is the Indian code for criteria for earthquake resistant design of structures for general provisions and buildings. So clause 6.4.3 of IS 1893 states that the effects of design earthquake loads applied on structures can be considered in two ways, namely equivalent static method and dynamic analysis method. We discussed about the equivalent static method design methodology in our first video lecture series of design of seismic resistant earthquake building or earthquake resistant RCC building, and that was the equivalent static method or equivalent lateral force procedure. And besides the static method, we also have dynamic analysis method. In turn, dynamic analysis can be performed in three ways, namely response spectrum method, modal time history method, and time history method. So there are various methods to perform a dynamic analysis in our building: response spectrum and time history method and modal time history method. So in this standard, that means in the IS 1893 code, equivalent static method, response spectrum method, and time history method are adopted. The code talks about these three design methodologies or these three design processes only. Equivalent static method may be used for analysis of regular structures with approximate natural time period less than 0.4 seconds. So only for regular buildings, that means the building in a building which is regular in plan and elevation, or a building which is irregular, which do not have any kind of irregularity including mass irregularity or stiffness irregularity or any other torsional kind of irregularity. Generally for such buildings and for low-rise buildings, equivalent static method is suitable and it is appropriate also. That means a linear static method is applicable to such regular and low-rise buildings for which the natural time period, approximate natural time period, is less than 0.4 second. And if we come across any irregular buildings or buildings in seismic zones with greater seismic hazard, then we have to perform dynamic analysis. And in performing dynamic analysis, one of the methods is the one that we are talking in this video lecture series, the response spectrum method. So what does the code say about the dynamic analysis method? In clause 7.7, there are provisions or criteria for dynamic analysis method. First, in 7.7.1, the code talks about the conditions in which dynamic analysis should be used or can be used. Linear dynamic analysis shall be performed to obtain the design lateral force for all buildings other than regular buildings lower than 15 meter in seismic zone 2. That means, first, if our building, the total height of our building is less than 15 meter and our building lies either in seismic zone 2 or seismic zones in which hazard level is lesser than that in this seismic zone 2, then we can use linear static method. Linear static method or equivalent lateral force procedure suffices. But if the height of our building is either if the height of our building is greater than 15 meter or our building lies in a different seismic zone, those seismic zones in which the hazard level is greater than that in seismic zone 2, that is seismic zone 3, 4 or 5, then we have to use linear dynamic analysis method. And that linear dynamic analysis method is used to design seismic base shear. It is used to obtain design seismic base shear and the distribution of that base shear to different levels along the height of the building. The analytical model for dynamic analysis of buildings with unusual configuration should be such that it adequately represents irregularities present in the building configuration. Not only for dynamic analysis method, for every type of analysis, when we are modeling the structure in our software, then we should try as much as possible that our model represents the real structure. And this modeling becomes even more important when there are irregularities present in our building. We have to try to model those irregularities as closely as possible to our real structure. And another important provision regarding dynamic analysis is dynamic analysis may be performed by either the time history method or the response spectrum method. When either of the methods is used, the design base shear VB estimated shall not be less than the design base shear VB bar calculated using a fundamental time period TA, where TA is as per 7.6.2. So let's see what this clause is trying to say. While performing equivalent static method, we calculated the time period of our structure based on formula that were given in our code. And these formulae are given in clause 7.6.2. We had the formula for time period of bare moment resisting frame buildings without any masonry infills, and we had formula also for buildings with masonry infill and for other types of structure. If you remember, we used this formula 0.075 into h to the power 0.75 for the time period calculation of our reinforced concrete moment resisting frame building, where h represented the height of our building. So suppose VB bar is the design base shear which we obtained from our equivalent static force method or our linear static procedure, and VB is the design base shear which we got when performing the dynamic analysis. In our dynamic analysis, let's just hear response spectrum analysis because we are concerned with only response spectrum method. So if this VB is smaller than this VB bar, that means the design base shear obtained from our dynamic analysis process is lesser than that base shear that we got during linear static method, then we should assume that at least this much amount, this VB bar amount of base shear acts upon our structure. Although from dynamic analysis we get a lesser value, we still have to design our structure for this minimum base shear, that is VB bar. So suppose we got from response spectrum analysis method, we got base shear to be 300 kilonewton, suppose. And equivalent static force method, we got base shear of suppose 450 kilonewton. Now from dynamic analysis we got a lesser value of base shear. Although this may happen, we still have to design our structure for this minimum 450 kilonewton base shear. And that's why before performing any other type of analysis, any other dynamic analysis, we first have to perform the linear static analysis for our structure. So it is necessary to perform a linear static analysis of our structure before performing dynamic analysis, because we have to compare the base shear that we obtain from dynamic analysis to the base shear that we obtained from our linear static method. So what happens? What do we do if our base shear from dynamic method is less than that from linear static method? So in clause 7.7.3, it also says that when this base shear calculated from dynamic method is less than the base shear calculated from linear static method, the force response quantities shall be multiplied by a factor, and this factor will be BV bar by VB. For example, So I talked about, suppose VB bar is 300 and VV is 450. Now we have to multiply all of our response quantities by this factor, 450 divided by 300. So the factor that comes from this 450 by 300, that factor is used to multiply every one of our response quantities, including base shear also. For example, our base shear is 300. Now if we multiply 300 with this factor 450 by 300, we get our new base shear or minimum base shear to be 450 itself. That is the same base shear that is obtained from equivalent linear static method. So we have to multiply all of our response quantities, including member stress resultants, story shear forces, base reaction, by this factor VV bar by VV. So in our IS 1893 code, what this is trying to say that our base shear calculated from dynamic analysis method should be at least 100% of the base shear obtained from equivalent linear static method. So in this also, when we multiplied 300 by this factor, we got the minimum base shear to be equal to the base shear obtained from linear static method. That means minimum base shear should be at least 100% of this equivalent static base shear. And in other codes, you may get that to be 80% or 90% or 95%. But in our IS code, it's our minimum base shear should be at least 100% of the base shear obtained from equivalent static force method. So for earthquake shaking considered around two mutually perpendicular plan directions x and y, separate multiplying factors shall be calculated. For x direction, VVx bar by VVx, and for y direction, VVy bar by VVy. And for vertical z direction, the multiplying factor should be maximum of these two factors. The maximum value should be taken. This process is known as the scaling of base shear or the rescaling of base shear. We will look at the scaling of base shear and how do we do the scaling when we come to the modeling part of this response spectrum analysis method. And finally, clause 7.7.5 talks about response spectrum method now. This up to clauses 7.7.3, these were for all the dynamic analysis method, including time history method. 7.7.5 talks particularly about this RSA method. Response spectrum method may be performed for any building using design acceleration spectrum specified in 6.4.2 or by a site-specific design acceleration spectrum mentioned in 6.4.7. I will come to this in our next few slides. Now, the design acceleration spectrum, we also looked something, we touched upon this subject during our first video lecture series also, how to calculate the design acceleration spectrum. For detailed explanation on these various factors, you can go to that part of our course and watch our videos there also. I will talk about in brief here. The design horizontal seismic coefficient AH for a structure shall be determined by using this formula. If you remember what we talked about an equation or an expression in which we said that the design seismic force is a product of this horizontal seismic coefficient AH into the seismic weight of the building W. We discussed in detail about the calculation of seismic weight in our first video lecture series. We also talked in detail about this design horizontal seismic coefficient, and the product of these two factors will give us the design base shear or the design seismic force. So this value of AH or the seismic coefficient is given by Z by 2, SA by G, and R by I. So the difference in equivalent static method and the response spectrum method while calculating AH is the calculation of this Yase by G value. Yase by G value, that means the design acceleration coefficient value. Other values are the same. Z refers to zone factor. It is given in table 3 in IS code. R refers to response reduction factor. It is given also in our code for different types of structures, and we will look in detail about this R in our one of our next slides also. I means the importance factor which is 1.5 for critical and lifeline structures, 1.2 for business continuity structures, and 1 for the rest. And the difference is only in the calculation of this Yase by G value. So calculation of Yase by G value, there are two sets of formulas. In number A, the calculation is given for equivalent static method, and in number B, the value is given for response spectrum analysis method. So let's look here. Yase by G is the design acceleration coefficient for different swell types. You can see here our formulas are different for rocky or hard swell sites, for medium stiffness swell sites, and for soft swell sites. And this Yase by G value is normalized with peak ground acceleration. That means our Yase by G value is divided by our ground excitation component. We talked about this in our previous slide. UZ double dot means our ground excitation or our ground acceleration value corresponding to natural period T of the structure. It shall be as given in parts 1 to 5 of IS 1893 for the corresponding structures, and when not specified, it is taken as that corresponding to 5% damping. So the value of Yase by G is dependent first on the rocky or hard swell sites, and that means it is dependent on the local swell conditions, and it is also dependent on the time period of our structure. So based on these two factors, we calculate the value of Yase by G, and then we calculate the value of design horizontal seismic coefficient. Now let's see here design acceleration spectrum or our elastic design spectrum. Before going into this graph, you may remember from our previous lecture or our first lecture of this video series, we talked about the response spectrum, and we talked about constructing our response spectrum based on the records of our previous earthquakes or based on our past history of earthquakes. And in that we talked about the 1940 El Centro ground motion, and we also saw a response spectrum based on that past earthquake. And if you look at the response spectrum for past earthquakes, you generally find that those are very jagged response or very irregular response. There is many number of spikes like this, and from these spikes you have to calculate the maximum response by finding the peak of those response spectrum. And these type of spikes, these are for a certain or a particular ground motion or a particular earthquake that has occurred in the past. Now what happens is that for the design of new structures, the response spectrum for a ground motion during a past earthquake is inappropriate. You cannot design a structure based on the response spectrum of a past earthquake. And why is it inappropriate? It is because this irregularity is the characteristic of only one excitation. This spikeness or this irregularity of our response spectrum, which we see for this one example, is only a characteristic of one excitation, and the response spectrum for another ground motion recorded at the same site during a different earthquake is also irregular. For example, if we have one site here, and if we want to calculate the response spectrum for this same site, but due to another different earthquake, then we may get something like this. Or If we consider a third earthquake and again draw a response spectrum, then we may get something like this. So the response spectrum in our site differs, and it is different for different past earthquake or past ground excitations. So you see that if you compare these, let me draw with another color here. So if you compare these three response spectrum, this green one, this yellow one, and this red one, what you see is that the peaks or the valleys, that means the maximum displacement or the maximum response of our structure, will not occur at the same time period. That means the situation of these peak values or the situation of these peak motions occur at different time period based on the different response spectrum. Also, for any particular site, we may not be able to draw or we may not be able to predict this irregular response spectrum in all its detail. So you see that firstly, due to the irregularity of this response spectrum, the peaks do not lie at the same time period, and also it is not possible to predict the response spectrum for any ground motion that may occur in the future. So we have to construct a design spectrum. This is the response spectrum. This is only a response spectrum of past earthquakes, but while designing a structure, we have to construct a different design spectrum. And that design spectrum consists of a set of smooth curves. You see here, now you can see in this figure 2, design acceleration coefficient ESA by G corresponding to 5% damping. This design acceleration spectrum is a set of smooth curves or a set of or a series of straight lines, and these response spectrum or this design spectrum curves are drawn for a particular level of damping. Here you see we have drawn this curve, or this curve is for 5% damping. This 5% damping is generally adopted in the design of our structures, and it is considered that this 5% damping is sufficient to represent the damping forces in all of our structures, including RCC or steel or masonry structures. So our design spectrum curve or our design spectrum consists of a series of smooth curves, and these curves are constructed for a particular level of damping. And here we can see that our curves are, we saw in our previous formula that our curves are dependent on the local site conditions and the time period of the structure. So in the x-axis we have the natural time period, and these three curves 1, 2, 3 represent three different types of soil or three different local site conditions. And how are these design spectrum curves constructed? This curve is constructed from ground motion parameters, and these curves are representative of ground motions that are recorded at the site during past earthquakes. We do not use the past earthquake response spectrum directly, but we only construct a design spectrum curve that are representative of the past earthquakes at that particular site. And what happens if we have no past earthquakes recorded at that site? Then we have to perform statistical analysis of ground motions at that particular site. And that statistical analysis includes different parameters such as the magnitude of the earthquake, the distance of that site from the fault zone, the faulting mechanism, and the local site conditions of the soil, local site conditions, and the geology of the travel path of seismic waves from the source to the site. So considering these different parameters, this spectrum is constructed for a particular site and based on those other similar sites also. We have to perform statistical analysis to construct these design response spectrum curves. And as we talked about, this bold line represents the spectrum for rock or hard soil. This comparatively middle, this middle line represents for medium soil, and this third line represents for soft soil. You see that for hard swell or for this rocky or hard swell, the buildings having the lower time period or higher frequency is more susceptible to this rock or hard swell conditions, because you can see here this graph represents for a rocky or hard swell. So the buildings with lower time periods are more susceptible to our local site condition, this rocky or hard swell condition. And similar is the case for the medium swell and soft swell. So this is our design response spectrum curve, and it is given for response spectrum method and given in our IS 1893 code clause 6.4. So I wanted to talk a little about a response reduction factor before moving on to the next slide. You saw in our formula for design horizontal seismic coefficient, it was Z over 2 SA over G and I over R. Let's go back to our previous slide. Sorry, it is R over I, not I over R. This is not I over R, it is R over I. And R here represents the response reduction factor. So what happens is that when we construct or when we model our structure linearly, or when we construct a linear model in our structure, certain factors such as the inelastic energy dissipation in our building or the damping energy or different types of ductility demand and capacity, these are not captured or these are not considered when we design or when we model a linear structure in our software or when we construct a linear model in our software. To capture all these phenomena, we have to perform a dynamic analysis, and that may be either time history analysis. Generally, time history analysis is performed for the structure when we want to capture all those phenomena. So when we are analyzing our structure, if we consider that our structure responds linearly and elastically, if we consider a linear elastic response of our structure to the earthquake loads, then the maximum force that is induced in the structure is very high. If we consider the linear elastic response for the whole period of any ground motion, then the maximum force in the structure is very high, and thus it becomes uneconomical to design the structure for such high elastic force. We have to design very large foundations. Our beams and columns should also be of greater cross section. So as a whole, it becomes rather uneconomical to design our structure for this maximum force or this greater force which occurs or which is induced in our structure if we assume linear elastic response. So what we can do instead of, or what we assume instead of taking for granted that our structure remains linear and elastic for the whole period of the earthquake, we can assume a non-linear response of our structure. And this non-linear response of our structure is due to different factors or due to different properties or due to different characteristics of our analysis models and of our structure. And this characteristic of our structure that allows us to design our structure for a lesser load as compared to this maximum elastic force, that factor is called the response reduction factor or R. And this response reduction factor accounts for three different phenomena. ductility, redundancy, and overstrength. Sometimes this ductility and redundancy are considered in the same category, that is only ductility. So our response reduction factor R is composed of two primary characteristics or two primary conditions, that is response reduction due to ductility, let us call this R mu, and a response reduction factor due to overstrength, R ohm. So response reduction factor accounts for the nonlinear response of our structure and thus the reduction in the maximum design force. So first let us see what is ductility. So what happens when our structure yields? As our structure yields, two main things happen. First, there is more energy dissipation in the structure due to hysteresis, and second, the structure becomes softer and its natural time period increases. So when natural time period increases, that means that the structure has now to resist a lower seismic force. The structure only has to resist a lower seismic force due to ductility. Higher ductility indicates that the structure can withstand strong shaking without collapse. This is the property of ductility because of the ductility nature or because of ductile detailing of our structure becomes able to withstand higher seismic force due to strong shaking. And even if our sections of beams or columns or even if our stiffness of our building is lesser compared to what is needed to withstand this maximum force, this phenomenon of ductility allows the structure to withstand higher shaking due to collapse. Hence, this phenomenon of ductility here in this diagram has reduced our maximum force from FEL to FY. So one phenomenon that accounts for our response reduction factor is ductility. And another two phenomenon is redundancy and overstrength. Or we can say this a single phenomenon of overstrength also. First, what is redundancy? Let's see. Redundancy means when our structure yields at one certain location. When our structure yields at one location, it does not mean that the whole structure has yielded. As you can see here, we have our first significant yield at this point, Fs, and our maximum load capacity is Fy. So if our structure yields at this point, the first yielding occurs at this point, this does not mean that our whole structure has yielded. Rather, after the first yielding, the load redistribution may occur in our structure. And load redistribution in our redundant structure provides additional safety margin. So because of this redundancy in our buildings also, we can assume that our structure is able to withstand a higher force. So due to redundancy, our maximum load capacity is decreased to, this Fy value is decreased to Fs. And finally, we can even decrease this Fs force on our structure to a lesser value, this design force. And this reduction is due to the overstrength property of our building. Overstrength means the members in our structure has reserve strength in themselves, and that contribute to overstrength of our structure. There are various factors that account for the yielding of a structure at loads higher than the design loads, and that are, firstly, we use different partial safety factors. We use partial safety factor for seismic loads, for our gravity loads, and also on our materials. That partial safety factor also means that we are designing our structure considering our members to have a, or our members are considered to have a lesser strength as compared to their actual strength. So in that case also we have reserve strength in our materials. Moreover, our partial safety factor on load means we are designing for a certain greater load than the actual load that may come to our structure. That also means there is some reserve strength also. And moreover, our material properties also account for overstrength, because one example is that we may use a member size of a beam or a column larger than that required, or we may use the value of reinforcement in our structure larger than that required. We perform ductile detailing and we confine the concrete in our structure. There is some confinement performed in while detailing of our structure, and that confinement of concrete also improves its strength. We may have strength contribution of non-structural elements. For example, if we are designing a moment resisting frame, there will be the presence of infill masonry walls. We do not consider the contribution of those infill masonry walls, and we consider them non-structural components in our building. But we considering that non-structural element does not mean that those infill masonry walls will not be contributing to the stiffness of our structure. Even the strength contribution of non-structural elements also contributes to the overall overstrength of our structure. And finally, our ductile detailing also adds to the strength. So all these factors contribute to the overstrength of our structure, and because of this presence of overstrength, we are able to reduce our design load from FS to FDES. So finally, what we see is that all three factors, due to ductility, redundancy, and overstrength, these factors are accounted in the response reduction factor. And this response reduction factor, because we are dividing this coefficient by response reduction factor, higher the response reduction factor, lower will be the value of this acceleration coefficient, and hence lower will be our design base shear. And from this graph also we saw that the response reduction factor allows us to decrease the maximum load coming onto our structure from FEL to DES. There is a reduction in the maximum earthquake design force. So this is the concept of response reduction factor. And finally, talking about other codal provisions, in clause 7.7.5.1, we have the number of modes of vibration that we should consider during response spectrum analysis. We will look at this. First, it talks about natural modes of vibration, then it talks about number of modes to be considered. The number of modes to be used in the analysis for earthquake shaking along a considered direction should be such that the sum total of modal masses of these modes is at least 90% of the total seismic mass. We talked a little about this modal mass participation factor in our previous lecture videos also. When due to the ground excitation, our building or our structure vibrates in a particular direction, not all the mass is contributing to that vibration. Only a certain amount of mass is contributing to the vibration of our structure in any particular direction, in any particular mode of vibration. And the total number of modes, such modes of vibration, because we talked about in our previous lecture that what response spectrum analysis does is it calculates the response of each mode of vibration, and it combines all those modal responses by using certain rule or by using certain formula. So to find the overall response, first we need to find the response of each mode of vibration. And how many modes of vibration to consider? Such that we have to consider that number of modes such that the total modal masses for those considered modes is at least 90% of the total seismic mass. And finally, 7.7.5.3 talks about the combination of modes. We mainly talked about three methods in our previous lecture: the complete quadratic combination method, the absolute sum method, and the square root of sum of squares method. So number 2, if building has few closely spaced modes, the net peak response quantity, we perform absolute sum. If the building does not have closely spaced modes, then we perform the square root of sum of squares, SRSS method. And the most generally used method is the complete quadratic combination or CQC method for the combination of our modal responses. So this is the formula for CQC methods. So these are three methods for the combination of modal responses. So this brings us to the end of this video lecture or this second lecture of this series. In this lecture, we talked about the Codal provisions regarding the response spectrum method. We also touched a little about response reduction factor. What is response reduction factor? We looked at a graph, and we looked at other provisions regarding modal combination rules and design horizontals coefficient calculation. So in our third lecture or in our upcoming lecture, we will perform this dynamic analysis, this response spectrum analysis in etaps. We will look at how to define the modal cases, or how to define our response spectrum function, how to define our response spectrum load cases, and we will perform the dynamic analysis. And after performing the dynamic analysis, we will look at about the scaling of base shear, which we talked about in this lecture also. We will see how to perform the scaling of base shear, and finally, after performing the scaling of base shear and analyzing the structure again, the design part is similar to our other methods, or the design is performed in same way as for equivalent static method. So we are left to see, or main things that we will do in etaps is first the definition of modal cases, response spectrum function, and load cases, and then we will see about scaling of base shear. We will see all that in our upcoming lectures. This is the end of our lecture 2. We'll meet again soon. Thank you.